Hello MUS 1002 students. In this video, I'm going to go over, microphones, and specifically how microphones work. So, the earliest likely example of a proto-microphone is Johann Philipp Ries's sound transmitter from 1861. This used a metal strip attached to a metal enclosed membrane that would vibrate. As the membrane vibrated, it would produce intermittent contact between the strip and the contact plate, causing amplitude changes in the form of electrical current. Next, we have Elisha Gray's liquid transmitter, a conductive rod in an acid solution attached in a circuit to a second rod connected to a battery. This yielded better results by changing the space between the two rods in proportion to a change in sound amplitude, or volume, that was measured as a change in electrical current. Alexander Graham Bell's patent for a very, very similar transmitter, the telephone, was actually submitted on the same day as Gray's submission for a patent caveat. They were both submitted March 10th of 1876. David Edward Hughes' carbon microphone from 1878, however, was the first device that could consistently carry intelligible speech and is generally regarded as the first true microphone. The carbon microphone used two metal plates separated by carbon granules. So a sound hits the outward-facing diaphragm, which makes it vibrate, and presses inwards towards the granules. The granules change the amount of electrical resistance between the plate, with higher pressure resulting in lesser resistance. A steady, direct, and not changing current is passed from the plate to the granules, and the change in resistance results in the output of a modulating or changing current that represents the change in sound pressure. Hughes' design would continue to be refined by others. Major improvements came first from Thomas Edison in 1886, followed by George Neumann, who would later found one of the major microphone manufacturers in 1925. And in fact, Neumann Microphones is still in business to this day. Other major developments led to the standard microphone types that we know and use today. The condenser microphone was created by E.C. Wendt for Western Electric in 1916. The moving coil or dynamic microphone was created in 1923 by H.J. Round for the BBC. It was significantly improved in the 30s by the legendary recording engineer Alan Blumlein. Then we have the ribbon microphone, created in the 1930s, probably by Harry Olson at RCA, but there is a lot of conflicting research about this. So we'll say probably by Olson. He seems like the most likely candidate. So how do mics work? All microphones are transducers. They convert changes in sound pressure level, which corresponds to amplitude or volume. This is changed to electrical current, generally through different means, but magnetic induction is very common. The output of a mic is a modulating electrical current that is extremely weak, and so you need to send it to a preamp to boost it up to a usable level where the changes are more apparent. The output of the preamp is then passed to an analog to digital converter, or ADC, that converts the analog electrical signal into digital data that can be stored and edited on a computer. All mics have three major parts: the capsule, the transducer, and the case. The capsule is an incredibly thin membrane of metal or plastic. Generally, it's going to be metal. In order to reproduce higher frequencies, it must be as thin as possible, because the thinner the capsule, the more it's susceptible to slighter changes of vibration, and the higher you can record. Unfortunately, this makes them incredibly fragile. But when the capsule is struck by sound waves, it vibrates in response, and these vibrations are converted to changes in electrical current by the transducer, which is protected by the case. As the capsule is so thin and sensitive, it is almost always covered by a grill, a metal mesh that helps to protect it. In addition to protecting it, the grill and the case have a noticeable effect on the directional response, how it picks up sound, and the overall quality of sound and the color of the sound of the microphone. Here's a picture on the left of a standard microphone grill. And then on the right, you have a picture of a microphone capsule. In this case, the center gold material is the diaphragm, which is being used to measure the vibrations. So let's talk first with the dynamic microphone, which appropriately is what I'm using right here. The dynamic mic is the most common type of microphone for live sound reinforcement. Dynamic mics work on the principle of electromagnetic induction. A diaphragm is attached to a magnetic coil, which is positioned in a permanent magnetic field. When sound hits the diaphragm, it vibrates, and the motion of the magnetic coil in the field creates a very weak electrical current. This then is boosted by a preamp and is recorded. But the fact that it is creating its own electrical signal means that the mic doesn't need electricity to work, and as a result, can get very close to fairly loud sound sources. And because it can only measure vibrations that are hitting it and is not trying to amplify anything else in its pickup area, it has a smaller pickup area, meaning it can minimize bleed or unwanted sounds from other instruments. The nature of the diaphragm, though, results in a significant drop-off in its ability to record frequencies above 10 kilohertz. So if you need higher frequencies, for example, a piccolo or a really, really high set of string harmonics, you're probably going to want to choose a different mic. Here's a quick photo. You can see the diaphragm here in this cross section is attached to the voice coil, and that is positioned directly over a magnet. These would be using the same magnetic polarity. So if it's a positive polarity on the coil, it would be a positive polarity on the magnet, because then as they push against each other, they move back into position, they push, they move, and that creates magnetic induction, which produces a very small electrical current. The ribbon mic is functionally very similar to the dynamic. Vibrations in the air hit a diaphragm, which vibrates inside of a magnetic field and produces a small electrical current that's boosted by a small internal transformer. However, the big difference is the nature of the diaphragm. Ribbon mics are called ribbon mics because of the fact that they use a small strip of an extremely thin piece of metal as a ribbon suspended in a magnetic field instead of the more traditional circular design that you would find on a dynamic mic. So this change in form to a ribbon does a couple of things. First, it makes it possible to record higher frequencies, typically up to 14 or 15 kilohertz, with a smoother roll-off of higher frequencies above that. They tend to sound very neutral, or what you hear is what you get, and they can take equalization extremely well. Also, ribbon mics, because it's a strip, you can pick up sound from either side. So they have a different pickup pattern than what you would expect on a dynamic microphone. But also like dynamics, ribbon mics can take very high sound pressure levels. However, there are downsides. The ribbon elements themselves are extremely fragile. Even touching it can probably destroy them, as will blowing too hard directly onto a ribbon element. They tend to measure their thickness in microns. So we're talking relatively, in proportion to the diameter of a human hair. Improperly storing the ribbon horizontally so that the ribbon is just going across, it can actually deform by gravity and start to bow, which will affect the frequency response. And most importantly, it's very important to know what type of ribbon microphone you're using. There are two types. There's active and passive. Active ribbon mics require electricity to operate, generally because they have better transformers and require more power in order to convert the signal from the ribbon into something usable. Passive ribbon mics, however, do not. And sending electricity in the form of phantom power or a battery-powered preamp to a passive ribbon mic, and especially the older ones, will very likely damage the ribbon. It can, in fact, explode the ribbon. So at that point, you have a multi-$1,000 paperweight in the form of a destroyed ribbon mic sitting on your desk until you can pay through the nose to have it repaired. Here's a picture of the ribbon element itself. The actual ribbon is the very thin strip of corrugated metal down the center, suspended between two very powerful magnets in the assembly. This is a very common way to structure the ribbons in an assembly like this. That way, if they do need to be replaced, they're easier in that you can slide out the assembly and then unscrew it and refit the ribbon. So we talked about active ribbon mics requiring power. This is generally in what's called phantom power form. And phantom power is an electrical signal sent through the microphone cable that's used to power microphones. It's generally between 24 and 48 volts, but 48 volts is common. In fact, on a lot of mixers, preamps, and audio interfaces, there is a plus 48V switch, which will apply phantom power. On most consumer-grade gear, this typically is applying phantom power to either all channels or to a set group of channels. On pro gear, it's toggled on a channel-by-channel basis, allowing you to mix and match different types of microphones. And this is very important to know. For example, my portable audio interface is generally, it's only 4 channels. It has one plus 48 volt switch that applies phantom power to all of those. So I could not use a passive ribbon on that with an active ribbon. On my studio interface, however, I can select which channel has phantom power out of all 16 channels. All condenser microphones require phantom power to operate, as do active ribbon mics. Passive ribbon mics and dynamic mics do not use phantom power. Again, if you send phantom power to a passive ribbon mic, you may blow it up. Dynamic mics, however, will not be affected. So if you have an interface that is either phantom on or phantom off and you need to mix condensers and dynamics, totally fine. You are not going to hurt the dynamic mic at all. But what is this condenser microphone I have mentioned? Well, it's the most common type of mic in the studio, hands down. Condenser microphones are microphones that work on the principle of electrical capacitance, and as a result, they are sometimes called capacitor microphones in older books. You have 2 plates that are electrically charged using phantom power, an external power supply, which is more common with vacuum tube-based mics, or batteries. 1 diaphragm and 1 fitted backplate are placed in very close proximity inside a ring inside the capsule. Sound waves cause the diaphragm to vibrate and move closer to the backplate, which creates a change in capacitance, which results in a voltage change, which is magnified by a transformer and output from the mic. Condenser mics come in 2 major types: large diaphragm, or LDC, or small diaphragm, or SDC. Both of these types can record the full range of sounds that the human ear can perceive from 20 to 20,000 hertz. So why are they called large and small? Well, small diaphragms typically use a diaphragm of 1/2 inch or less. Large diaphragms typically use anything larger than 1/2 inch, but 1 inch is generally the most common diaphragm size. The larger diaphragm of a large diaphragm condenser requires that it be placed in a grill for protection, but these grills also tend to color the sound by partially reflecting the sound as it comes in. It hits the diaphragm, it might bounce off, hit the grill, come back, hit it again. The result is that you have a slight amount of filtering and almost implicit reverberation that generally sounds a little bit warmer due to the larger capsule and the grill's tendency to color the sound. So this makes large diaphragm condensers an excellent choice for voices, solo instruments, especially strings like violin and cello, as overheads for drum sets as well, and anytime where you want kind of a larger than life type sound. Small diaphragms, however, almost always have the diaphragm facing directly out of the body of the mic, similar to a dynamic mic. As a result, they don't have a grill that's really covering the diaphragm in the same way, so if sound hits it, it just bounces back out into space. This makes them less susceptible to coloring effects, and as a result, they're very, very good at picking up very quick and short sounds and are extremely neutral sounding, which makes them an excellent choice for recording an entire group of people. For percussion, especially if you're recording drums in isolation and you really want to get a nice whip crack snare. Or any sounds that require being as pure and natural as possible. So I've done projects where I've recorded voices for machine learning projects. And we always used small diaphragm condensers for those, just to get everything as pure as possible. Now, there are some downsides to condenser mics. Unlike dynamics and ribbons, they are very susceptible to humidity and temperature changes. And if the humidity is too much, the capsules may stick together and they might stop working. But more importantly, because they have electricity going through them, it's creating a very large pickup range. They are extremely sensitive to even very small changes in sound pressure levels. So when you're recording with condensers, bleed from other instrumental sources is inevitable and it is noticeable. Finally, condensers tend to be a you get what you pay for type item. You can go on eBay or Alibaba or eBay and get a cheap condenser mic for under $50. I don't recommend doing it, however. Cheap condensers are inconsistent from mic to mic, even from the exact same manufacturer, the exact same model, even if they have sequential serial numbers. This means that it makes stereo recording very difficult, where you want the mics to be factory matched to within very, very tight spec of each other. High quality condenser mics can easily reach into the thousands of dollars for a single mic, but they sound terrific. And vacuum tube based mics can get into the tens of thousands of dollars, especially for vintage mics, like if you're trying to track down a vintage Telefunken U47. I hope you have a very large bank account. It's a great mic. It was the favorite of Frank Sinatra and Frank Zappa, but those older ones, because they were all handmade, have a certain sonic characteristic the new ones just don't, and they command extremely high prices as a result. And here is a picture of a prototypical large diaphragm condenser microphone. This is the Mojave 301. You can sort of see the capsule coming through the grill. It has switchable polar patterns on the front. It also has a built-in high-pass filter and a decibel pad switches which cannot be seen that are on the back. Solid mic, but don't drop it on your foot. You are liable to break a toe. But that leads into a discussion on polarity and microphone pickup patterns. So the polarity, the polar pattern, the pickup pattern, or the polar response, all synonyms, determine how well a mic will pick up sound coming from different locations around the capsule. Typically, this is shown on a two-dimensional polar plane. By convention, the mic points straight up at 0 degrees, with 90 degrees corresponding to the right of the capsule, 180 behind the capsule, 270 to the left, although some manufacturers may reverse this and go 90 degrees to the left. Just be aware that microphones exist in 3 dimensions, and so you're picking up sound in 3 dimensions. But in general, you can interpret these polar charts as showing both the horizontal and vertical plane. There are 4 major polar patterns for microphones that you need to be aware of: omnidirectional, figure 8, cardioid, and hypercardioid. Omnidirectional or omni pattern mics pick up sound from all directions around the capsule. They respond more or less equally in 360 degrees to any sound. Dynamics and condenser mics can use this pattern, and it's kind of a favorite for specialty mics like lavalier mics that you clip on to your lapel when you're doing an interview. It's a really good pattern choice for close miking sources because it avoids the bass boost known as the proximity effect that all other microphone patterns have when placed close to a source. And generally, it's a relatively natural stereo sound when you use a pair of Omni mics and space them out. You get what's called the spaced pair or spaced Omni. So here's a picture of a polar plot for the Omni mic, and you can see it's just a circle. That is all it is. It's picking up perfectly in 360 degrees around the mic. Figure 8 mics pick up sound in front and behind the capsule due to the nature of the polar pattern, but they tend to reject sounds coming from the sides, making them really good for minimizing bleed from side sources. This makes them a really good choice to record amplifiers from a band with a little bit of forethought in terms of how you're setting up the amplifier placement. The pickup areas to the front of the mic is going to be a little bit brighter sounding than the pickup area to the back, as the back tends to pick up reflections of sound as they reverberate through the room instead of the direct sound source. But functionally, you could turn it around and you'd get the same thing. It would just be that the back would be slightly brighter this time than the front. All ribbon mics are fixed in a figure 8 polar pattern due to the nature of the ribbon element. Most high-end condenser mics can be configured to use this pattern as well via switches, or on vacuum tube mics, you just slowly turn a knob and it changes the pattern and actually morphs between Omni to figure 8 to different patterns. It's very cool, in fact. And here is a picture of the figure 8. You can see I've got a lobe pointing up to 0 and another lobe going down to 180. But it's pretty good at rejecting the sides at 90 degrees and 270 degrees, which makes it a really, really nice choice, again, for amplifier work. The next pattern is the cardioid pattern, which is the most common polar pattern, bar none. Cardioid mics pick up primarily to the front and the side in what looks kind of like an inverted heart-shaped pattern. It does include bleed from the sides, but the cardioid pattern offers superb rejections of sound behind the mic with a true null point where you will not hear any sound at 180 degrees behind the capsule. So this makes it a great choice to avoid bleed from a source behind the mic, particularly in live sound situations like stage monitors that are placed at the front of the stage so that the band can hear themselves. You give the singer a cardioid pattern mic, and as long as it's pointing towards them, it will not pick up the sound coming from the monitor wedges at the front of the stage. As I said, this is the most common polar pattern, so unless it's otherwise specified, it is safe to assume that a dynamic or condenser microphone is probably cardioid. And here is a picture of the cardioid. And you can see it's got great back response. Again, it looks like an inverted heart. And at the V in the heart, that is a true null point. Finally, we get the hypercardioid or supercardioid pattern. Same thing, different names. It's a variation on the cardioid pattern, but the lobe of the heart shape is noticeably thinner, meaning it has a much more pronounced directional response to the front of the capsule and better side rejection than cardioids. Unlike cardioids, there is no true null point behind the capsule. In fact, hypercardioid mics actually will detect sound in a small area behind the capsule, similar to a figure 8 mic, but with a much smaller pickup area. It's not a particularly common pattern, although I am, in fact, using a hypercardioid pattern on this mic that I'm recording with. And it can especially be found on specialty instrument mics, like the DPA 4099, which is a favorite mic of mine to use on guitars, mandolin, ukulele, trumpet, saxophone. They are great mics for that purpose. You can also find this on higher-end condenser microphones as a switchable option. And that's a picture of it. But, of course, there are also some microphone accessories. Just having a mic is usually not enough to get a good recording. There are some extras that you will want to have. All mics require an XLR cable to connect to a preamp or to an interface. You will also generally want shock mounts. These are little elastic cages that hold a mic in place on a stand and minimize vibrations coming from the floor up into the stand or handling noises. None of those are things that you want to record. You will also want to use windscreens. These are small foam covers that go over the grill and protect the capsule from the motion of air currents indoors, like AC units in particular, as well as air from the singer's mouth. Typically, they go over the grill, although this mic that I'm using, it is placed inside of the grill. If you're recording outside, you will want what's called a dead cat filter, so named because it looks like a cat that's been run over. Just a tube that you slide over the mic, covered in fuzzy hair, that reduces turbulence from wind when recording outside. Here is a picture on the left of the XLR cable. Note that it has 3 prongs that it uses to connect. It carries ground on one, and then it carries a balanced signal. So there are actually 2 copies of the signal from the microphone going. So if something happens, you can swap the pins and still get a signal. On the right is a shock mount. It just suspends the mic in an elastic band that reduces those vibrations and keeps it from recording any handling noise. Very, very handy device. Then down here on the left we have the typical foam windscreen, and on the right the dead cat filter. In fact, there are a number of different similar filters that come in a variety of sizes. They are generally referred to with dead names as well. I've seen very small ones called the dead kitten filter. I have seen the largest one is the one for the Rode blimp. It is called a dead wombat because, well, they're an Australian company and because it's gigantic. Finally, there is one other accessory that we should talk about, a pop filter. Pop filters are a very common accessory used in studios to help protect large diaphragm condenser mics, or any mic in effect, from air and the occasional bit of spit from vocalists. By limiting the amount of air that passes through, it helps keep plosive consonants, your P's, K's, F's, S's, B's, D's, hard consonants like that, from popping on the recording. It protects the capsule of a condenser in particular from moisture and humidity, and I have found that placing one is a good way for dealing with singers who want to eat the mic, which does happen, sadly, and they need to be dealt with so that your very expensive condenser microphone does not have a capsule problem because it has been touching the back of their throat, or otherwise having a humidity problem resulting in a stuck capsule. And here is a pop filter. They just attach to the mic stand and use the gooseneck to position it in front of the mic. Typically, it is a thin nylon piece of fabric stretched over the hoop, but you can also find them in metal as well. SE Electronics makes a nice dual element one where you can easily add metal or nylon and have both, or swap out one for the other. But a very, very good device to have. It just makes it one step less that you have to do when you're editing the recording later on.